Let's see what you thought about. What kinds of things did you think about that would be advantages of making parts this way? Yeah.
Cheap and fast.
Cheap and fast. So in some ways, cheap and fast. For what? What about it is fast?
You have like a set of molds that you just fill, close, like cool, you just open up and get them out.
Okay.
You don't have to machine something every time to make a part, it's just a reliable mold every time.
Okay, so it gives you the rough shape of the part very quickly, and so this is a pretty complicated part. It would take a long time to machine, and maybe it is a lot faster to do with casting. It will find out that if you do die casting, which is very much like injection molding, you can create parts very, very fast. And so if you ever had Hot Wheels or Matchbox cars, they were always die cast for the body of the car. They're about the only thing that I can think of that brags about it. But anyway, yeah, so it's good for that. What else? Yeah.
Relatively low person hours per part. Like it might take a while for the mold to cool, but because the molds are cheaper, if they're taking a long time to cool, then you can have several molds and have somebody cycling through.
Okay, yeah, so it can be fairly low people hours per part. It depends a little bit on what type of casting you're doing, but yes, in general, it is lower people hours per part. Yeah.
You use less metal. There's like a lot of cavities in there that if you machine them, you just lose that metal.
Yeah, it seems like that would be true. And in one way it is. For that part, there's less metal used. But when we actually go and create the molds, we'll find out that because we have to have risers and we have to have the sprue and we have to have all these other things, we actually end up with a lot of extra metal used. Now it can be reused, but we paid to heat it up and cool it down one time. Okay? What about disadvantages?
That is not a precise part.
Not a precise part, okay. The precision on the parts is different, yeah, just depends. Yeah.
I was going to say, if you're working with an alloy, you have to be kind of observant with those slushy zones and those cooling behaviors. Otherwise, if you're looking for a uniform material, you may end up with that like allotropic diffusion, or just parts coming out and having a non-homogeneous mixture.
Yeah, so that was a really nice way of saying it. I would put it as the material is generally crappy.
Yeah.
So all the reasons that you said are exactly right. And it is hard to get good material when you cast. And so very often you cast it and then you have to do follow-on processes to force the material to be the way that you want it to be.
I was just going to piggyback and say, like, you can take a piece of billet that's like x-rayed and know exactly what it is, and you're cutting exactly what you get. Like, you know, like in terms of like machining.
Okay.
This, it's like, you might get exactly it, but there could be weird little porosity bits.
Yeah, there are all kinds of things. When you actually go and you try to machine these, you'll hit little pockets that are open, you'll hit little nubbins that are super hard, where stuff just gathered together and made a really hard point in it. It's easy to ruin tools. Yeah, the material is kind of wild. And so I think that is the takeaway from what we're talking about right now, is that we have all of these processes going on in the heating and cooling, and we've got things diffusing back and forth, and we have solid transformations going on where it's changing phase, or it can even change structure completely. And all of this is going on in the material as it's trying to cool, and it can lead to all sorts of challenges. So it's a great way to make parts. It's used a lot, especially with the secondary process. So yeah, something like this would be crazy hard. I mean, there's a lot of time in this if you were going to machine this part, and there's all kinds of complexity in here that you can create relatively quickly and easily. And this one's got, because this is the kind of casting that uses a styrofoam as the pattern, this one's really cool because it still has the the styrofoam look to it. It looks like the whole thing's made of styrofoam. It's pretty neat. But anyway, yeah, so there's good and there's bad with it. You don't know a lot about metal. Your mouse. Oops, that was the wrong place for the mouse. That's a better place for the mouse. Yeah, yes.
How does the styrofoam not melt when you're casting?
It does. That's
Oh,
actually the good thing. So what you do with this, the way that you do this is you take a piece of styrofoam that you have cast in a mold. So you actually cast the styrofoam in a mold to get this shape. Usually, and that mold can be anything. It can be metal or wood or whatever the styrofoam will cast in. And then you take that styrofoam part and you coat it with ceramic, and you put a bunch of coats of ceramic on it, and then you have a place that you can pour into it. This one was separated right here, so the metal flowed in right here. And then as the hot metal flows in, it burns the styrofoam out of its way. You can also use it with 3D printed parts, but with 3D printed parts, you create the ceramic and then you have to melt the plastic out of it beforehand. We will try that again this year. Last year, our success was poor.
Wait, so then it's just ceramic with the styrofoam in it, and then you just pour it in. So there's like technically a little bit of burnt styrofoam in there.
Yeah, there's a little bit of polystyrene running around, but this is at such a hot temperature, it mostly produces that as gas, and then that gas comes out vents in the mold.
Okay.
All right, so just to remind you, as this is happening, say we have something like we have a 50-50 mixture of two materials. So this is kind of the easiest case, two materials, 50-50 mixture. As it is cooling and we cross the liquidus line, at the beginning, the material that solidifies is 36% copper and 64% nickel. So that first little inner part that's nucleating has a very high amount of nickel. And then as the material continues to cool and it continues to grow on those nucleated points, the material there, as it's cooling, will have a different, it's down to 58% nickel now, and by the time you get to where there's almost no liquid left, we are down here, and so this is 50-50. So the thing to know with that is that each little place that it starts to nucleate may have a different ratios of the materials at its core than it does at the outside of the grain. Now eventually that will equalize out through diffusion if you leave it at temperature long enough, but the other thing that happens is if you leave it at temperature a long time, the grains get really big, and if the grains get really big, then the part is very low strength. So there are just all kinds of things going on inside the material, and that makes it hard to get good material when you are cooling it. There are a bunch of other things that happen. Come on. There we go. But first, we're going to do a quick review of a bunch of things, just to make sure that we're keeping up. Difference between strength and stress.
Strength is a specific type of stress.
At which?
At which there's a change.
Yes, at which a change occurs. So a strength is a stress at which a change occurs. Very good. Ductility, what is it? What are two ways to measure it?
Wait, could you repeat that between stress and strength?
Yes, the difference between stress and strength. A strength is a stress at which a change occurs. It is a specific stress. So like the yield point or the ultimate tensile or failure. Yes?
We do percent reduction of area.
Okay, percent reduction of area or percent elongation. So you can either stretch it or you can look at the amount, or you stretch it and you either look at the change in length or the change in area. Okay, those are the two ways to measure it. What does it mean? Yes?
The amount of strain that can be put into a material before fracture.
Okay, the amount of strain that you can put into something before fracture. How much can you change the shape? So we're gonna talk about the ductility of materials and say that it's got like 0.1 or 0.2 ductility, or that can also be 10% or 20% ductility. And if we have a material that is a super material, it may be like 30, 40, 50% ductility. But we have methods that we can use to get beyond those numbers.
Wait, so what are the 2 weeks tomorrow?
We'll get to it later, yeah.
Okay, thank you.
Yeah, so just review. So, oh, that's a good point. On any of these slides that I have a bunch of questions like this, if you look at the slides that are online, the speaker's notes are on those slides, and the speaker's notes have the answers to all the questions. So when you, this is sort of a, hey, these are good things that you should know if there were going to be a test in 4 weeks, 3 weeks, something like that. And so you should make sure that you know these. Yes?
Are the tests gonna be multiple choice or free response?
They are mostly free response, yes.
And also, sorry, can you repeat the definition of ductility?
Ductility is the amount of strain or shape change that something can endure before failure. What is CISA-P? Specific heat, all right, and what does specific heat mean? Yeah?
The amount of energy per mass that it takes to heat up?
Okay, the amount of energy per mass that it takes to heat the material by 1 degree. So kilojoules per kilogram per degree Celsius. Interstitial and substitutional. Yes?
It's the substitutional one is when it happens when the solvent and the solute, the radius of the molecules are within 15% of each other, so not that big of a difference, and it just replaces one. And then the interstitial is when the solute atoms go in between the solvent ones because they're much smaller.
All right, yes. And so interstitials are really small. They can diffuse through the crystalline structure pretty quickly. Substitutional cannot. Are crystalline defects in common metals bad or good? Depends. It can't depend.
It's good for some
That's
properties
like an
and bad
answer
for other
that a
properties.
faculty give. You're not allowed to. That's yeah. Okay, say that again.
It's good for some properties and bad for other ones. Like it strengthens some parts of it.
Okay.
And weakens other parts.
Okay.
That's the right word.
All right. It does depend. In a lot of ways, you get more strength from defects, but it ruins the ductility. And so you cannot strain the material as far before failure if it has more crystal defects. So anyway, yes, it does depend. That's right. What is a slushy zone? What does it signify? Eutectic, we just talked about that. What are important things I can learn from a phase diagram? You know, you can't learn everything. I cannot find someone's address. I cannot find out if there are more birthdays on September 9th than any other day. All right, what can I learn from a phase diagram? Yes?
The temperatures at which a material will change from liquidus to a slush or to a solid.
Okay, so I can look and I can see the temperatures at which something changes, phase, and also potentially, and that is both from a liquid to a solid and phases within the solid even. So it can change structure and phase as well there. Yeah, fine. Good, we just talked about that. So here's what I want you to do. With 1 or 2 people around you, I want you to take out a piece of paper. You're eventually going to turn this piece of paper in. So find one that you can take out. Yes?
Individually or for the both of us?
You need 1 piece of paper for the group. Yes, so for the both of you. And here's what you are doing. We have I mean, the elements are not all listed on the periodic table. It is missing two. They're in the lower right-hand corner. But there is Belling and Ham that are part of the periodic table in this class. So they're both metals, and they have a eutectic composition of 60% Ham. There's a solubility limit of 10% on both ends. And the melting temperature of Belling is 350 C, Ham is 300 C, which is clear if you have ever put it in the oven. The solidus temperature of Bellingham is 150 C, and I want you to draw a eutectic phase diagram for Bellingham. I want you to identify the phase fields, and we're going to call the solid solution of Belling alpha and the solid solution of Ham as beta Ham. And we want you to indicate the composition ranges for hypoeutectic and hypereutectic alloys. Excellent. Go.
Okay.
I've got mine.
On the bottom, it's usually what, the
Do you have a solid